first of all, showing you the response with 20 kilohertz. This is basically we have an ID probe. Again, this is one of our detachable ID probes. The head's movable. This is good because you can either have the probe fail or the cable fail, and you can swap one or the other out, which is the kind of thing you need when you're working on site. And also, obviously, you can have different size probes and collection of cables of different lengths. The probe is set currently to 20 kilohertz in bridge. If I place it into the tube, find somewhere to balance, press the balance button, and let's go through the tube. There's a big, large 20% OD groove on the outside. It's off screen, but not to worry about that. There's some 20% flat bottomed holes here, and 80%, sorry, 20%, 40%, 60%, 80%, and then there's a through hole. And one of the things is that we set the wobble signal that you get as you're rumbling alongside the tube kind of horizontal, so that the noise coming off the inner surface of the tube, caused by the drawing process mostly, and that ends up with a defect through hole being at 45 degrees. And then on the inside of this tube, both at the far end, let's go up to here, there is an internal groove that gives a roughly almost horizontal response, but it's very near the end of the tube and the probe is coming out. So that's at 20 kilohertz. So if you use a high frequency, you get more phase shift, but obviously you're less sensitive to OD defects, and use low frequency, make the phase shift left. But at the moment we've got pretty much 90-degree phase separation, which is one of the ways of setting the equipment. And that's basically it is. So you can test many types of tubes, from heat exchangers in chillers to condensers in large power stations. One of the drawbacks is that the tubes are normally, well, the tubes are non-ferrous, and this only works on non-ferrous tube, by the way. There is a support plate signal caused by support plates, the ferrous support plates along the length of the tube, and they give this sort of more like an open figure of 8 signal, which is quite different in characteristics to the defect. But if you're looking at and analysing, this can sometimes be difficult, and particularly if you have the defect by the hole. Now you have a strange loopy signal caused by both together, and one of the ideas is to use dual frequency to remove the effect. And we'll demonstrate this in a second. So using ID probe settings with 20 kilohertz bridge, this is the let's go. Okay, so what we're seeing here is that's the drilled hole, through drilled hole, 80%, 60, 40, 20, and another 20 groove, 20 set of holes, and going up back to the end here, and then this is support plate signal. Okay, now one of the big applications for dual frequency is to remove support plates because they cause quite an annoying signal. Here I've positioned it beside the drilled hole, and you'll see that that's kind of obscures the through hole. So if we could clear that up, that would be a great advantage. So how to do that? Well, here we have channel 1 set to 20 kilohertz, and I've now set channel 2 to 30 kilohertz, so 20 kilohertz, 30 kilohertz. If I now go down here and display the channel, I can have 2 traces. This is the 2 support plate signals. I'll get a slightly diminished signal and phase shifted at the higher frequency of the 30 kilohertz than the 20 kilohertz. But I've set the signals so that the drilled hole of both the two frequencies is identical. And if I now go down the tube, you'll see as I go along that the phase gradually separates, that the higher frequency moves faster than the right, so it ends up on the right. Quite a subtle change, but that's quite a useful change as it happens. To mix, we have on this instrument some functions called mixers. The easiest way to demonstrate what's going on is to go to the mixer channel, go down, display the channel before the mix. So what we've basically done here is to go back to the main screen. Maybe I won't, just for reasons of clarity, go down here. So I'm not showing the actual original signal or channel 2. What we've done is we've put that into a phase and gain shift block, and I've made, let me go and move the probe to the end of the tube, and I've made the responses from the 20 kilohertz channel look as close to the 30 kilohertz channel as possible by manipulating the phase and gain on the 30 kilohertz channel only. So now we've got two comparable signals there, and then mixing basically is subtraction of these two signals. The quick way of showing that is now if I go down, switch off the display of the mix before subtraction, go down the bottom, and now switch on the mix channel. What I've now got is the yellow signal is the residual signal from the mix, and the green signal is the original 20 kilohertz signal. So how does that now look versus the holes? And if I now go along here, so that's residual, this is a drilled hole, so see the drilled hole still coming up. In fact, the signal's slightly larger. We're getting phase shift as before. And now if I go and put the signal part thing, we can see, if I go and disable the green channel to stop it being confusing, go and not display that. Now that's the hole, and that's the support plate. I think you'll agree that now you can quite clearly see the drilled hole beside the support plate.